Hello everyone, welcome to the 2.8 lecture devoted to spin caloritronics. And in the previous lectures here, when we were talking about spin injection, we discussed a way how you can create spin polarized current or spin current, simply sending a normal electric current through B layer of magnetic metal, non-magnetic metal. And in the previous lecture, we were talking about spin pumping, where you could create a spin polarized current simply by exciting magnetization precession in magnetic layer, and this automatically induces spin polarized current into the attached normal metal layer. And today, we will learn how to create spin polarized current using simply thermal gradient. Before we will go to this fancy interesting phenomena, let me say a few words about the classical Seeback effect. So as you all know, when we have a conductor and place it in a thermal gradient, then you will get a voltage will be generated. And so there will be difference in potential between these 2 points of a conductor. And this effect is named as Seeback effect. And efficiency of this effect is defined by so-called Seeback coefficient, which you can simply define the magnitude of voltage you obtained, you divide it with a thermal gradient, and this defines your coefficient. Physically, this Seeback coefficient is a function of density and scattering rate of the conduction electrons in metals. Having this effect, what we usually do afterwards, we put 2 different metals with different Seeback coefficients together in such a way that they both have the same temperature on one side and the same temperature on the opposite side. And then because we have difference in the Seeback coefficients, and namely in the voltage, then we will get here a voltage which will be a measure of the difference in temperature. Or what you can also do if you want to measure absolute temperatures, in principle, you just need to have a reference point in one of the points. For example, you can put it in the water with ice, then you will always have here 0 Celsius, and then you can measure relatively precisely temperature in this point. So this is named thermocouple, and thermocouple is used nowadays in for measuring of temperature. Okay, and before we'll move on, let us have a look briefly on this nice video, which clearly demonstrates what is Seeback effect.
Here we will demonstrate the Seeback effect by using a thermoelectric effect demonstrator and 2 cups. As you can see, one is labeled cold and the other is hot. The cold cup already has water inside. After we place the demonstrator inside the cups, we will pour in the hot water. Now both legs are immersed. One leg is immersed in the cold water and the other leg is immersed in the hot water. As the heat flows through, it will create a current that will produce electricity. What makes this possible is the Peltier module that's between the 2 metal legs. After a short while, we'll notice the propeller will start spinning. And there it goes. Generally, you can generate electricity from every available temperature differential, but with a small differential, the generator power will also be small. So if you were to put cold water with ice on one side and boiling water on the other, it will result in more power being generated. Now let's remove the legs from the liquids and place it on the table. As you can see, it is still spinning. Now the Seeback effect is the production of an electromotive force and consequently an electric current in a loop of material consisting of at least 2 dissimilar conductors when 2 junctions are maintained at different temperatures. The conductors are commonly metals, though they may not be even solids. In around 1821, the German physicist Thomas Johann Seeback discovered the effect, which now bears his name. The Seeback effect is commonly used to measure temperature with great sensitivity and accuracy, and to generate electric power for special applications. Now the propeller will spin for a little short while, and if you have this at home you can test it and time it, but I wanted to show you on the back side behind the motor there is a switch here. Now what that switch is for is if we click it to the other side, the propeller will stop spinning. As you can see, it's not spinning anymore. So what this does, it reroutes the electricity from going to the motor, and it reroutes it to the contacts, so you can measure the electricity using a multimeter. So that's also interesting as well. So thank you for watching our video, and check back for more videos.
From this video we learned that you can get electricity in such a simple way, so you don't need battery to spin your propeller. So it was a nice break, and now we are coming actually to spintronics back, and we want to speak about spin Seeback effect. So spin Seeback effect, as opposite to classical Seeback effect, is very new comparatively. So it's a group of Iji Saito, Professor Uchida, he's now, and the idea is, again, it's like it was in Hall effect, spin Hall effect. That's why this name is here. You can immediately guess it, that now instead of creating placing your conductor in a thermal gradient and obtaining here electric current, what you do, you take your conductor, place it in thermal gradient, but instead of spin current, instead of charge current, you will get spin current. So it means that electrons will spin down, will start to move here towards higher temperature, and spin up will move in the opposite direction. So there will be spin polarized current simply formed along this conductor. Yeah, and the main idea behind is very simple, that like here we have different Seeback coefficients in the thermocouple, different metals. Here we just have a different Seeback coefficient for electrons with spin up and for electrons with spin down. And then we will get kind of a thermocouple effect, but instead of charge current, we will have spin polarized current. So it means that in this case, the thermal gradient will create some difference in magnetic moment between spin up and spin down electrons, and this spin polarized current can be detected again in a form of inverse spin Hall effect, like we considered in the previous lecture. Yeah, and here in this slide is just again repeated that what we know already, as that in the case of heavy metal with large spin orbit interaction, you can make conversion between spin polarized and charge polarized current, because charge current is always easy to measure in the form of voltage again. And how experiment was performed. The first experiment in this pioneer paper was done in the following way. There was a metal permalloy thin film, which was placed in thermal gradient from one side to another, and then here on top were placed such a contact pads, such stripes of platinum with good interface in between to ensure proper spin mixing conductance. And what happened, there was a generation of spin polarized current, and principally there were two currents generated. One was generated here into platinum, and then where temperature was higher, and then due to inverse spin Hall effect, so we know inverse spin Hall effect, for example, it's shown here, that when spin polarized current goes from interface up, like in the case of spin pumping, then electrons are scattered to one direction, and you can have measure voltage in this transverse direction. But here on the other side, where its temperature is lower, you can have the opposite effect. It means that now spin polarized current has opposite sign. In some sense, it's injected from your platinum into the permalloy, and this you can easily detect simply because now electrons, so this JS spin polarized current is pointing down, and it means that electrons will be scattered into the opposite direction, like it's shown here with this blue arrow, and that means that now you measure again difference in electric potential, but with the opposite sign. Okay, and how this this effect was originally detected. It was such a permalloy strip with two platinum layer from one side and from another side, where temperature is high, temperature is low. And then what you see in this graph, it's a simple voltage measured here. So it was inverse spin-Hall voltage measured at one side and measured on the opposite side as a function of the thermal gradient. And so here's the difference in temperature between sides at 0. Here they're going up to around 20 Kelvin. And you see that from one side, when you apply thermal gradient, you will indeed observe the generation of voltage, but it will be negative. So it means that increase in thermal gradient results in the increase of voltage, but with negative sign. And if you measure from this side, from the hot side, then increase in temperature results in the positive inverse spin-Hall voltage, and voltage again linearly increases. So that was very simple detection, and in order to prove that this is really a spin-Seeback effect, not just thermocouple, also they performed additional experiment when they measured voltage potential between the sides of permalloy without using some platinum, and as you see, there was no voltage detected. If to speak about classification of spin-Seeback effect, nowadays we define two main types of Seeback effect. The first one is transverse, and second one is longitudinal spin-Seeback effect. So transverse Seeback effect means that your thermal gradient applied in plane, and then spin polarized current injected up or injected down will be perpendicular to the direction of thermal gradient. And in the longitudinal geometry, spin polarized current is parallel, therefore it's named longitudinal. And in this case, again, you can create injection of spin polarized current from your magnetic metal into your normal metal, usually with large spin orbit interaction. In one direction, if the bottom you have higher temperature, and at the top you have low temperature, thermal gradient like this, and spin polarized current is injected up, and you will measure some voltage. But if you will switch the direction of thermal gradient, so it means that on top you will have hot system and bottom you have cold one, then spin polarized current will be injected into the opposite direction. Yeah, just technical two words. So principally, transverse geometry is a bit harder to measure because in experiment, when you're trying to create such a thermal gradient here, it is really hard to avoid formation of parasitic gradient in the perpendicular direction. Therefore, while performing this experiment, one have to make sure that there is no parasitic gradient perpendicular to the stack. And it's a bit more complicated to perform this kind of experiments, but these are very trivial and works very reliable, what we also seen in our lab many times in different configurations. So here you see the definition of spin-Seeback effect. This effect which refers to the generation of spin voltage caused by a thermal gradient in a ferromagnet. And it's very interesting that although originally spin-Seeback effect was discovered for magnetic metals, then pretty often people tested it with magnetic insulators, with yttrium and garnet, and have found that it also works. And in the case of magnetic insulator, one explains it in terms of phonons. So since the temperature difference applied to YIG here results in a phonon flow. And these phonons consequently are coupled to magnons in yttrium iron garnet, and this magnons then induce spin polarized current into the attached metal. And this induction you can understand, for example, in terms of spin pumping, as we discussed, because spin pumping, when you excite magnetization precession, you also will induce spin polarized current into the attached metal. As we all know, there is an effect which is just opposite to the classical Seeback effect, and it's named Peltier effect. Idea is very simple. If you will take the same thermocouple, but instead of placing different parts of it in different temperature and measuring voltage, what you do, you can send current, you can apply voltage, and then it will generate a difference in temperature. For example, most of these experiments to measure spin Seeback effect and so on were performed using classical Peltier element. So this is a simple, it's commercially available, it's very simple and cheap. You can buy it, and if you need to vary temperature, let's say from 10 degrees of Celsius up to 100 degrees, you can easily do this with Peltier element, and that's what we pretty often use in lab. And in the same way, like there is a spin Seeback effect, there is also so-called spin Peltier effect. And in spin Peltier effect, we speak about voltage which drives a current in platinum, like it's here. And then we know that since this is a heavy metal with large spin orbit interaction, what we will get a spin polarized current in the direction perpendicular to it. And this spin polarized current then will induce through spin transfer torque magnons into the system. And just opposite to this case, since magnons are coupled to phonons, in such way we will generate a flux of phonons, which can be described simply as a temperature difference. So the idea of this effect is very simple. You just apply current, you create spin polarized current, and as a result, you will measure a difference in temperature. And this is a very nice and very simple experiment where we have combination of spin Seeback effect and spin pumping. This is principally, that's one-to-one the same experiment which I explained to you in the previous lecture, at the very end of the previous lecture about spin pumping. So you have yttrium iron garnet, you put platinum 10 nanometer thick, and then what you do, then you will put, for example, Peltier elements, one here, you can create thermal gradient. And then depending if you have thermal gradient 1 up or down, if field is applied like that, then on these two contacts, you are measuring voltage. In one polarity or another polarity when you switch either direction of applied field or you switch direction of the thermal gradient. This is a classical spin Seeback effect, but if we are coming back to that experiment devoted particularly to the spin pumping, investigation of spin pumping plus inverse spin Hall effect, then in that simplest experiment, you also always have spin Seeback effect, which we at some point have realized, but it's weaker, but still very detectable. Because what you have when you want to excite magnetization precession in GIG, remember there was this antenna through which we sent 7 gigahertz frequency, and we excited magnetization precession. But then we had to tune field, and only at some point we reached the resonance conditions, and it means that our applied microwave signal started to transfer its energy into GIG, into the magnetization system, excited magnetization precession, and then we measured it in a form of inverse spin Hall effect. And this is exactly what you see here. So there is this very narrow band of fields when you can excite magnetization precession, and you see such a large inverse spin Hall voltage created by spin pumping. Then what you do, you switch polarity, you go to the opposite field, and again you will see inverse spin Hall voltage already with opposite polarity since you changed the direction of field, and it's here. But after looking more careful to the experimental results, we have realized that we see this plateau here and here. And this plateau is nothing else as spin-Seeback effect. Because if you are applying microwave signal, so you do not switch it off, it's still there, apply to antenna, but you do not reach resonance conditions, you still have parasitic heating up of platinum due to Joule heat. And in this system, you create a situation that platinum is hot, YIG is cold because it's insulators, there are no eddy currents. So it means that for all these fields here, and for all fields sludges and resonance, we will create a thermal gradient in the direction that platinum is hot and YIG is cold. And then it means that it also will induce spin polarized current and also will be measured in inverse spin Hall voltage, like it's shown here. But of course, in the case of spin pumping, you induce spin polarized current from YIG into platinum. So YIG is the source of current. And in this case, since platinum is hot, you induce spin polarized current from platinum into YIG. So these two spin polarized currents for spin pumping and spin Seeback effect have opposite signs. And that's exactly what you see in this picture. Is that here polarity, you have small signal, but it has negative polarity, and spin pumping signal has opposite polarity, so it's positive. And then when you go to zero fields, here you will get the main state. So there will be no clearly defined vector H, there will be no clearly defined vector sigma, which gives us spin polarization. Therefore, here will be some domain point, and at zero field we will cross simply to zero. And then you need some small few times Ørsted to magnetize your sample in the opposite direction, and then you just have symmetric picture, asymmetric picture with respect to this one. So this is such a very simple experiment which just proves how robust and principally very pronounced the effect is. And then there was this nice paper where many different groups performing this kind of studies performed the same experiment. So here you see Garchen, so Sebastian Gönnenwein, Rudolf Gross, Kaiserslautern, so I was on the spin pumping side, with Burkhard Hillebrand, Vitaly Vasyuchka, Alexander Sergava investigating spin caloritronics phenomena. Sindai, it's E.G. Saito group, Groningen, it's Bart van Wies, and of course Gerrit Bauer was here, who provided theoretical support. And the idea of this paper was to reproduce the same experiment in different labs and to see if everything agrees, if sign of spin Seeback or spin pumping or inverse spin Hall voltage doesn't change, and so on. And then it was very nice that principally there was perfect agreement between all experimental results. And if you would like to get the most checked information about the three vectors, which one is spin polarization, another is spin polarized current, and the third one is charge current or thermal gradient, then this is a paper I can recommend you. That's it. So this part was rather short. The idea was just to give you a brief understanding how else you can create a spin polarized current in the system. I hope you enjoyed, and we are ready to switch to the magnetoresistance phenomena.